We're going to be reading chapter 28, section 3, the Sun, Earth, Moon system, found on page 758. The relationships between the Sun, Moon, and Earth are important to us in many ways. The Sun provides light and warmth, and it is the source of most of the energy that fuels our society. Additionally, the Moon rises tides in our oceans and illuminates our sky with its monthly cycle of phases. Every society, from ancient times to the present, have based its calendar and its timekeeping system on the apparent motions of the Sun and Moon. Daily motions. The most obvious pattern of motion in the sky is the daily rising and setting of the Sun and Moon and stars and everything else that is visible in the sky. The Sun rises in the east and sets in the west. So do the Moon, planets, and stars. Today we understand that these daily motions result from Earth's rotation. The Sun, Moon, planets, and stars do not orbit around Earth every day. It only appears that way to us because we observe the sky from a planet and that rotates once every day or 15 degrees per hour. But how do we know that Earth is rotating? Earth's rotation. There are two relatively simple ways to demonstrate that Earth is rotating. One is to use a pendulum, which is a weight on a string of or wire that is suspended from support and can swing freely. A Foucault pendulum, which has a long wire and a heavy weight, will swing in a constant direction. But as Earth turns, it appears from one point of view that the pendulum gradually shifts in orientation. With a Foucault pendulum, pegs are often placed on the floor in a circle so that as Earth turns, the pendulum shown in figure 2812 eventually knocks over each of the pegs. The second method of demonstration that Earth rotates makes use of the fact that flowing air and water on Earth are diverted from a north-south direction to an east-west direction as a result of Earth's rotation. This diversion of direction is called the Coriolis effect, which you learned about in chapter 12. The length of a day as we observe it is a little longer than the time it takes Earth to rotate once on its axis. This is because as Earth rotates, it also moves along in its orbit and has to turn a little further. The time period from one sunrise to sunset to the next is called a solar day. Our timekeeping system is based on the solar day, annual motions. As you know, the weather changes throughout the year. The length of days varies, and temperature may range from cold to hot, depending on the latitude where you live. These annual changes are the results of Earth's orbit motion about the Sun. The plane in which Earth orbits above the Sun is called the ecliptic, as illustrated in figure 2813. The effects of Earth's tilt. Earth's axis is tilted relative to the ecliptic at approximately 23.5. As Earth orbits the Sun, the orientation of Earth's axis remains fixed in space so that at one point the northern hemisphere of Earth is tilted toward the Sun, while at another point, 6 months later, the northern hemisphere is tipped away from the Sun. Our seasons, as discussed in chapter 14, are created by its tilt and the Earth's orbital motion around the Sun. As a result of the tilt of Earth's axis and Earth's motion around the Sun changes its altitude in the sky. The way in which altitude of the Sun is measured is illustrated in figure 2814. You've probably noticed the change in altitude of the Sun during the northern hemisphere summers, when the Sun appears higher in the sky than it does during the northern hemisphere winters. This change occurs gradually throughout Earth's orbit in a cycle pattern, solstices. Earth's varying positions and its orbit around the Sun and the tilt of Earth's axis are illustrated in figure 2815. As Earth moves from position 1 through position 2 to position 3, the altitude of the Sun decreases in the northern hemisphere. Once Earth is in position 3, the Earth's altitude starts to increase as Earth moves through positions 4 and back to position 1. Position 1 corresponds to the Sun's maximum altitude in the sky in the northern hemisphere. At this position, called the summer solstice, the Sun is directly overhead at the Tropic of Cancer, which is 23.5 degrees north latitude, as illustrated in figure 2816a. On the summer solstice, which occurs around June 21 each year, the number of daylight hours of the northern hemisphere is at its maximum, while it's at its minimum for the southern hemisphere. During the summer solstices, the sun does not set in the region within the Arctic Circle, and it does not rise in the region within the Antarctic Circle. Conversely, when Earth is in a position 3 and the northern hemisphere is tilted away from the sun has reached its lowest altitude in the sky. At this position, called the winter solstice, the sun is directly overhead at the Tropic of Capricorn at 23.5 degrees south latitude, as illustrated in Figure 2816b. On the winter solstice, which occurs around December 21st each year, the number of daylight hours in the northern hemisphere is at its minimum, while it is at its maximum for the southern hemisphere. During the winter solstice, the sun never rises in the region within the Arctic Circle, and it never sets in the region within the Antarctic Circle. You will model the sun's position as seen from your location during the summer solstice in the mini lab on this page. Equinoxes. At position 2 and 4 in Figure 2815, Earth's axis is not pointed at the sun. As a result, both hemispheres receive equal amounts of sunlight, and the sun is directly overhead at the equator. Thus, the lengths of day and night are equal to both the northern and southern hemispheres when Earth is at position 2, called the autumnal equinox, illustrated in Figure 2816, and position 4, called the vernal equinox, illustrated in Figure 2816d. The term equinox means equal nights. At the Tropic of Cancer or Tropic of Capricorn, the sun is 23.5 degrees from the point directly overhead during the equinoxes. In the science and math feature at the end of this chapter, you will learn how Eratosthenes used the sun's position, that shadows, to calculate the circumference and the radius of Earth. Figure 2817 illustrates how the sun would appear in the sky to a person at 23.5 degrees north latitude during the solstice and the equinoxes. As you can see, the position of the sun affects how directly sunlight strikes Earth. When the sun is at a lower altitude, the sunlight that strikes Earth is spread out over a large area, phases of the moon. Just as the sun appears to change its position in the sky, so too does the moon. This is a result of the movement of the moon around the Earth and of our changing viewpoint of Earth relative to the sun. The sequential changes in the appearance of the moon are called lunar phases, shown in Figure 2818. You have learned that the moon does not emit visible light. Instead, we see that the moon's reflection of the sun's light. When the moon is between Earth and the sun, however, we cannot see the moon because the sunlight side is facing away from us. The dark moon position between Earth and sun is called the new moon. As the moon moves along in an orbit, as illustrated in Figure 2819, the amount of reflected sunlight that we see increases. The increase in the portion of the sunlight side of the moon, as we see it, is called waxing. When we can see less than half of the sunlight portion of the moon during this increase, it's called a waxing crescent. When we see more than half of the sunlight portion of the moon during the increase, it's called a waxing gibbous. Between these phases, the moon reaches a point in its orbit when we see half of the sunlight side. This is called the first quarter. As the moon continues farther in its orbit, it moves to a position where it once again aligned with the sunlight. This time, Earth is between the moon and the sun, and we are able to see the entire sunlight side of the moon. This is known as a full moon. Once a full moon is reached, the portion of the sunlight side that we see begins to decrease as the sun moves back toward the new moon position. The decrease in the amount of sunlight side of the moon that we see is called waning. As in the waxing phases, there's a period during the waning phases when we see more than half of the sun portion of the moon, as well as a period when we can see less than half of the sunlight portion. These phases are called waning gibbous and waning crescent, respectively. In the middle of the waning phase, the moon is in position in its orbit where we can see half of the sunlight portion. This is called the third quarter. Synchronous rotation. You might have noticed that the illuminated surfaces of the moon always looks the same, as the moon orbits Earth and the same side faces Earth at all times. This is because the moon is rotating with a period equal to its orbital period, so it spins exactly once each time it goes around Earth. This is not a coincidence. Scientists theorize that Earth's gravity slowed the moon's original spin until the moon reached synchronous rotation, the state of which its orbital and rotation periods are equal. Motions of the moon. The length of time it takes for the moon to go through a complete cycle of phases, for example, from one full moon to the next, is called a lunar month. The length of a lunar month is about 29.5 days, which is longer than 27.3 days it takes for one revolution or orbit around Earth, as illustrated in Figure 2820. The moon also rises and sets 50 minutes later each day because the moon has moved 13 degrees in its orbit over a 24-hour period, and Earth has to turn an additional 13 degrees for the moon to rise. Tides. One of the moon's effects on Earth is the formation of tides. The moon's gravity pulls on Earth along an imaginary line connecting Earth and the moon, and this creates bulges of ocean water on both the near and far sides of Earth. Earth's rotation also contributes to the formation of tides, as you learned in chapter 15. As Earth rotates, these bulges remain aligned with the moon, so that a person at a shoreline on Earth's surface would observe that the ocean level rises and falls every 12 hours. The sun's gravitational effect on the formation of tides is about half that of the moon's, because the sun is farther away. However, when the sun and moon are aligned along the same direction, the effects of the sun and the moon combine, and tides are higher than normal. These tides, called spring tides, are especially high when the moon is nearest Earth and Earth is nearest the sun in their slightly non-circular orbits. When the moon is at a right angle to the sun-Earth line, the result is lower than normal tides, called neap tides. Solar eclipses. A solar eclipse occurs when the moon passes directly between the sun and the Earth and blocks our view of the sun. Although the sun is much larger than the moon, it is much farther away, which causes the sun and moon to appear to be the same size than viewed from the Earth. When the moon perfectly blocks the sun's disk, we see only the dim outer gaseous layers of the sun. This particular site shown in Figure 2821 is called a total solar eclipse. A particular solar eclipse is seen when the moon blocks out a portion of the sun's disk. The difference between a particular and a total solar eclipse can be explained by the fact that the moon casts a shadow on Earth. This shadow consists of two regions, as illustrated in Figure 2822. The inner portion, which does not receive direct sunlight, is called the umbrella. People who witness an eclipse from the umbrella see a total solar eclipse. People in the outer position of the shadow, where some of the sunlight's reaches, are in the penumbra. They see a particular solar eclipse where part of the sun's disk is still visible. Typically, the embryo shadow is newer, wider than 270 kilometers, so a total solar eclipse is visible from a very small portion of Earth, whereas a particular solar eclipse is visible from a much larger portion. The effects of orbits. You might wonder why a solar eclipse does not occur every month, as the moon passes between the sun and the Earth during a new phase. This does not happen because the moon's orbit is tilted 5 degrees relative to the ecliptic. Usually, the moon passes north or south of the sun, as seen from Earth, so no solar eclipses take place. Only when the moon crosses the ecliptic is it possible for the proper alignment for a solar eclipse to occur. But even though it is not enough to guarantee a solar eclipse, the plane of the moon's orbit also rotates slowly around Earth, and a solar eclipse occurs only when the intersection of the moon and the ecliptic is in a line with the sun and the Earth. Hence, the proper alignment for solar eclipse does not occur every month with each new moon. Not only does the moon move above and below the plane of the Earth and the sun, but also the moon's distance from Earth increases and decreases as the moon moves in its ecliptic orbit around Earth. The closest point in the moon's orbit is called perigee, and the furthest point is called apogee. When the moon is near apogee, it appears smaller as seen from Earth, and thus it does not completely block the disk of the sun during an eclipse. This is called an annular eclipse because from Earth a ring of the sun called an annulus is visible around the dark moon, as seen in Figure 2823. You'll experiment with the different types of solar eclipses in the problem-solving lab on this page. A lunar eclipse. A lunar eclipse occurs when the moon passes through Earth's shadow. As illustrated in Figure 2824a, this can happen only at the time of a full moon. When the moon is in opposite direction from the sun. The shadow of Earth and the umbral and penumbral portions, just as the moon's shadow does. A total lunar eclipse occurs when the entire moon is within Earth's umbrella and the totality lasts for approximately 2 hours. During a total lunar eclipse, the moon is faintly visible as shown in figure 2824b because sunlight that has passed near Earth has been refracted by Earth's atmosphere. This light can give the eclipsed moon a reddish color as Earth's atmosphere bends the light in the umbrella and then the umbra, much like a lens. Like solar eclipses, lunar eclipses do not occur every full moon because the moon in its orbit usually passes above or below the sun as seen from Earth. Solar and lunar eclipses occur in almost equal numbers, with slightly more lunar eclipses. The maximum number of eclipses, solars and lunar combined, that can be seen in a year is 7. The last time this occurred was in 1982, and it won't happen again until 2038.